But anyway, so what Walt Thiel figured out was, okay, yeah, you get a 50% jump in performance, but because of the size and the drag penalty, we're only going to use hydrogen in upper stages. Once your first stage fires and drops off, you're high in the atmosphere, almost in vacuum. And so you don't have to worry about drag as much because you're already over the atmosphere, and you don't have to worry about temperature as much because you no longer get convection. Once you're in a vacuum, you can keep things very cold for very long periods of time. And so that was pretty much the pattern for the next, for the last, from about 62, the first hydrogen flight, to today, that people have avoided hydrogen in first stages. Now the shuttle has a hydrogen first stage, so is the Ariane 5. However, they also have these solid rocket boosters. And the solid rocket boosters are basically what's pushing you for the first 2 minutes. The core stage, for example, on this Ariane 5, that core hydrogen engine, that's providing like a few % of your thrust at liftoff. It only really becomes significant after the 2 minutes when you're through the atmosphere. One group didn't want to go that way. Boeing built the Delta IV, and they said, you know what? We're going to go for that 50% efficiency gain, and we're going to live with the drag penalty because, you know what? We have one pair of fuels on the pad. The first stage and the second stage, they both burn hydrogen and oxygen. Great. Less hassle, less equipment, less gear, less checks. It'll be cheaper. Unfortunately, Delta IV, well, for a bunch of reasons, pushed out of the commercial market. The only competitive role for the Delta IV is government launches because the government is bound by American provisions. So the Delta IV has you consider it a market failure, strictly for government launches.
And what makes it more expensive, the cost of the fuel?
Well, there's a whole bunch of things. It's just a lot of the T's didn't get crossed and a lot of the I's didn't get dotted that other manufacturers didn't. And yeah, they decided to go with hydrogen in a first stage where most people said, well, not really worth it, not really worth it. Some bad business decisions too. So yeah, I'll cut them some slack. Hydrogen was just one of the issues. Now, I've told you about the Army groups, the Navy groups. Air Force is not going to be left behind when it comes to rocket fuels. But what a lot of people don't realize is just how big of a program the Air Force can really sink into these things. So 55 U-2s are overflying the Soviet Union and other hostile states. The backers, the proponents of the U-2 thought it was an uncatchable plane. It was so high that not only could you not shoot it down, a few people even claimed that radar didn't even get that high. Well, I think Gary Powers demonstrated that U-2s are catchable. So within the Air Force, they had already been looking at, okay, well, what beats the U-2? It will become vulnerable at some point. We need to be thinking, okay, what's the follow-on after the U-2? And a massive project was started, Project Suntan. Many of its details are still black to this day. No one has a handle on how big the budget was because it was stashed in a whole bunch of funds to conceal them. So Project Suntan had hydrogen burning engines. Because you get that jump in efficiency, maybe not 50% in this particular case, but a big jump in efficiency. And also, when you're traveling at Mach 3, you heat up the airplane. The nose and the edges of the wings might actually glow red. And so the liquid hydrogen at hundreds of degrees below zero would not only be the fuel, not only would it be the coolant for the plane, but as you boiled the hydrogen at the leading areas of the plane and in the engine, you actually exploited that boiling, and you turned your turbines with boiling hydrogen. 2-for-1 deal. Oh, let me get in on that 50% gain. So the way you get energy out of a chemical reactions is that atoms swap electrons with each other. So hydrogen has one electron, and so it can participate in chemical reactions just like any other chemical. But since the hydrogen is an order of magnitude lighter, the hydrogen will then shoot out the back much faster. 1/2 mv squared, but because hydrogen is so light, that's a disadvantage in terms of drag, but it's an advantage in terms of thrust. Well, unfortunately, Suntan never flew. The Air Force range specification was 1,700 miles. Suntan, maybe 1,200 tops, and its own designer pulled the plug on it. Just said, no, this is not working, folks. Head designer was Kelly Johnson, the famed Lockheed designer. So after Suntan, what happened? Kelly Johnson abandoned hydrogen fuel, and then he went on to build the SR-71. You may have heard of it, but very successful and not burning hydrogen. And much more recently, we got a new development, hydrogen submarines. Who would think? Works in a blimp, works in a submarine. How does that work? Okay, so here you have your German Type 212 submarine, and it has related classes for export, and the Russians also have the Lada class submarine. But what do you need a submarine? You need some form of propulsion that doesn't involve air. Now in a fuel cell, if you're already bringing along the hydrogen or some other fuel with you, well, then you have tanks, and you can just add on a couple more tanks for your oxygen. Presto, underwater propulsion. And here, you can just barely make out in this construction shot 2 gas tanks on the top of the submarine. Inside, okay, so there's an outer hull of the submarine, an inner hull, that's where the actual equipment is, and you flood or empty the space between the 2 hulls, and that's what gets you, that's what makes you either float or sink. Since you have this incredibly strong metal hull that can withstand the pressure at these huge depths, stick some tanks in there. Sure, yeah, well, okay, we'll put some tanks in that space. We're not really worried about weight on the submarine. They're already bound by these 2 holes inside and outside. So you can have these incredibly strong tanks where you could just ram in massive quantities of hydrogen at just incredible pressures. Pressures you're not going to see out of a car, like 1,000 atmospheres.
So this is gaseous hydrogen, not liquid hydrogen?
Yes. 427F in air conducts away your air conducts heat, and it boils your hydrogen. Water will boil you right there. So yes, it's tanks of gaseous hydrogen, not liquid. And also, water everywhere, but not a drop to drink. What does the crew drink on a submarine? They're surrounded by seawater. Now, carrying seawater from home port, well, yeah, it's certainly doable, but it's really cumbersome. It's bulky. Trying to purify seawater, well, yeah, it's also possible, but a different set of hassles. There's no real good opportunity. So if you can have your propulsion system also provide some drinking water, not all of it, but some of it, even better. Wow.